Uh, this chapter is 12. It's 3 pages. So okay. In Korean, 삼상회로. The base is translated in Korean is 상. In generally, we have a one source like that. This is, for example, 200 cosine 2 pi 6t. This is a 60 hertz. Actually, no, I will give you an example. This is general 220 volt 60 hertz in the grid, the voltage source. You can get this voltage in the outlet in home and office and everywhere in Korea. Because this is only one voltage source, and this is a one voltage source. And because of the voltage is kind of potential difference, we need a 2 wire. We call this is a single phase circuit. In Korean, 단상회로. Then what is a 3 phase? We call this is a phase. This also is a phase. Then what is a 3 phase? 3 phase is a 3 dependent source, like way. Here and here. And this voltage difference is this is very important. And this time here the voltage, I will give you this. The polarity of this is minus and this is plus, and then this voltage is the same magnitude, Cosine, same frequency. And we have adding. Like that. And another phase is like that. This voltage is same magnitude, cosine, same frequency, and like that. And we call this voltage is A phase voltages, and this voltage is B phase, and this voltage is C phase. There are 3 phase. Circuit consists of 3 voltage source and each voltage magnitude is identical. That means we define this voltage is VAS, this voltage is VBS, this voltage is VCS. The magnitude of VAS, VBS, and VCS in generally, but the phase angle is 120-degree difference among three AC voltages. So this is 0 degree, and this is minus 120, this is minus 240. So this is a 3-page second. So if you draw the voltage here, like that, the A phase has a cosine here, so it looks like that here. Something like that. This is a VAS. When you define why we call this as VAS is terminal we call this as A, and the terminal we call it as B, and the terminal defined with C, and this point is a common point we define this as S. So VAS means voltage difference between A and S. VBS means voltage difference between B and S. And VCS means voltage difference between C and S. So we define the voltage name is VAS, VBS, VCS in this manner. So this is a VAS. Then VBS is a 120 degree. That means this is a angle here. So this is a VBS. This is a VBS. And VCS has a one more delay here. So this is a VCS. So the voltage phase difference between in the A and B is 120 degree, and phase difference between B and C is 102 in degree, and phase difference between C and A is also 102.20 degree. And they have the same magnitude. We call this waveform, this is a balances three-phase voltage source. Balance means when you define VAST, and I will use another things. VAST defined is magnitude of VAS cosine omega t plus A. VST has a VBS cosine omega t plus theta B, and VCS is V magnitude of GS cosine omega t plus theta C. Then balance means magnitude of VAS, magnitude of VBS, magnitude of VCS is same. And phase difference to A minus phi B, and phase difference to B minus B should be this 120. Actually, we have one more things. C minus A is 120 degree. Then we can say this is a balance. This is a balance condition. So we call this is a three-phase circuit. We connected this three-phase source. So I will give you introduce how to make a three-phase. So I will give you simple explain how to generate three-phase the voltage source. So, we know that the Faraday's law what is that? I already told you when you study the coupled inductor, we have a coil here. This is a little coil here, and there are the magnets, and there are magnetic flux here. Then in this area, the time variation of the flux make a voltage in this wire. This is a Faraday law. In the same way, we have one coil here in this way. It's a coil. So we have one rotating permanent magnet. This is rotating here. This fixes. This is rotating the low. It's N. Then there will be some flux. Then we will move this magnet in here. Then this magnet moves like that. This N, then flux will be here. Because of that, flux will move in this manner. So in the time domain, in this area, flux is varying. So we define this line, this point is A and A prime. So the voltage is induced by loss linkage. So we define the A prime is N dt d phi. So it's the same thing. We tell you the Faraday's law. But in this time, we make a coil, something like that. We have a same coil. We have a coil here, like that. Now I want to draw some circle. There. And we have also another coil. This is 120, 120, 120. We have another coil here. And also we have another coil here. And you find this is A prime, B prime, C prime. And we place the magnet here. Is N S. Then this magnet rotates in this way. This coil is, 3 coils. Has a same, 120 degree displacement. The same winding number. Then if VA prime is a Vm cosine omega t, then this omega t with omega is a rotating speed, repeating angular speed of magnet. Then VB prime, the induced voltage between in this difference, will have same magnitude, but this plus go here and go rotating here and then here. When same phenomenon happens, B phase winding after 120 degrees later, when the A phase winding has that phenomenon. So it has a cosine omega t minus 120 degree. So same reason, VCC prime is a same magnitude, cosine omega t minus but minus 240 is the same with plus 120. So we like to use the phase angle. So if we replace, express this is phasor, then VAA prime is VM 0 degree. VB prime is VM minus 120, and VCC prime is VM plus 120 degree. Because this is a balanced voltage. So if you draw the pairs diagram, voltage, we draw this manner. This is A phase here. This is A prime. And where's B? B is here. Same magnitude, but 120. VB, B prime. And C is in this direction. C prime. This is also 120 degree. The sequence is important. This A phase, this A, next B is plus here, and this is a C. So this is a balances the voltage. The very important characteristic of the balance voltage here is, I will write here, if 3 pairs has a voltage, if in the case of parentheses 3 pairs voltage is a VA prime plus VB prime plus VCC prime, always 0. This is an important characteristic of a balanced 3-phase voltage. If it does not balance it, then this is not satisfied. So, I'm confused with little thing. We define this is VAS. I define this point as S, but you can define this is not S, this is N. In general, this one not confused. This is N. N. This is better to understand. Only move. I will take it. This is N. Actually, S is okay. N is also okay. It depends on you, but N is more the general symbol to represent that point. So I will follow that symbol. This is N. Okay. Now I will give you a definition of neutral point. In Korean, 중성점. In some cases, we define that as an N, or in another case, we can define the S. It depends on, it's not important. But anyway, we have three, from this circuit, we have 3 voltages here. And from this process, we have three voltages. From here, we have three voltages. A prime is Vm cosine omega t, Vb prime Vm cosine omega t minus 120, Vcc prime is Vm cosine omega t plus 120 degree. Then we have three independent voltage source. So we have three things. That means we have one voltage. This is A and A prime. This is a B and B prime. This is a C and C prime. And we connect, and this is the negative polarity point in each other in this manner. So the point we define, and we call this point is neutral point. In Korean, 중성점. Then we'll connect this here. I will give you another example. I will change the notation here. I mean, it's not even anyway. Define this as A and B, A, C. I will change the things. This is B prime B. This is C, C prime. Then C. And so from these we get the three independent voltage source. From that, just connecting in this manner. We gather the three phase, the voltage source in this manner. So we call this is a phase, A phase, and we call this is a B phase, and call this is a C phase. So instead of VA prime, we can do VAN, and this is VB prime is VBN. So VCC prime is VCN. So we call this as VAN. We call phase voltage is VAN, VBN, and VCN. And we have one more, the physical things. We call this the line-to-line voltage. Line-to-line voltage in Korean. 선간전압. In Korean is 상전압. Why we call this line to line? Because I want to know the voltage between this terminal and this terminal voltage here. So this voltage is VAB, means voltage difference from B to A. Therefore, VAB is a VAN minus VBN. Same way, we have VBC is a VBN minus VCN, and VCA, this is important, the sequence is important. The VCN minus VAN. So this is the line-to-line voltage. Line-to-line voltage. The line-to-line voltage has a very special, very specific characteristic compared to the phase voltage. There's a difference. And magnitude difference. Between phase voltage and line-to-line voltage. Let's define the phase voltages. Okay, here VAN is VAN 0 degree. VBN is VM 1 minus 120 degree, and VCN is VM 120 degree. Then line-to-line voltage VAB is VAN minus VBN. So it will be VM 0 degree minus VM minus 120. And then there will be VM minus VM minus 0.5 minus J 0.866. So it will be square 3 VM 30 degree. The same reason, VBC is a square 3 and VM to this 30 degree minus degree 11 here, and VCA as a so we got it. The line to line voltage as a magnitude is square 3 times of VM, and phase is lead 30 degree compared to the phase voltage. So if you draw the phase diagram of this, you find this is A, more simply, A and B, VAN, VBN, VCN. Then VAB this is a VAB. So we get it here. This is a VAB. In the same way, this is a VBC. And this is a VCA. The angle is 30 degrees and magnitude is √3 Vm. This is a pale diagram of phase voltage and the line-to-line voltage. It's very important. And you need to familiar with this relationship between the line-to-line voltage and phase voltage. Line-to-line voltage is magnitude of line-to-line voltage is higher by 1.717. The square √3 is a 1.313, 717, and the phase lead in 3 degrees. So this is a 3-phase voltage here, and we connect this source. I will give you one more things. From here, we get 3 different voltages, 3-phase voltages, and from that, we have a connect in this manner. I will introduce the delta connection. So from this circuit, we get a VA prime, VB B prime, VC C prime. This also has the same magnitude and 120 degree phase angle difference. So we connect in this source in this manner. We have 3 voltage source. We call it 3-phase. This connection we call this is a Y connection. In a similar way, we connect this source. So in this manner, we define plus minus. This is A and A prime, and we have a similar source in this manner. It's B prime. We have a source in this manner, C prime, and connect in this 2-port and 2-port and 2-port, and define this is A, and define this is a B, and define this is a C. And then we have 3 points here. We have 3 points. This is A and B and C. I think it's like simple. It's more clear. Then the voltage source make the voltage difference between the line A and B. So we call this connection is delta connection, or we can represent delta connection. So here, in the case, we define that the voltages in phase voltage and line to line voltage, and we also can define the current here. In this manner, the current here is we define IA, and this current is IB, and this current is IC. And the current flowing through line is the same with the current of this current. The same. This is IA, this is IB, and this is IC. But in the delta connection, a little bit different, because this is IA, this is line current, this is IB, is line current, and this is IC, line current. But flowing through this source is different. So this is a little bit different compared to the source in the Y and delta. So we define the current here is IAB, and this current is IBC, and this current is ICA. We define current in this manner. I think the definitions are different. This will be like that, like that, like that. So in delta connection, there are two voltages, two current, the IA, IB, IC, and IAB, IBC, and CA. We will deal with about the relationship between the current and voltage in the case of delta connection. We will deal with this later. So I will do the circuit with the load in the case of three-phase the voltage source. 12 and 3, the Y to Y circuit. That is a simple. Now we have three voltage source, balance source. In this manner, it's Y connect configuration. This Y connections. You define this terminal is A, this terminal is B, and this terminal is C. And we define this is small n. We define this voltage is VAN, this voltage is VBN, this voltage is VCN. So we have like that. Like that. And there are load. The same configuration is Y configuration. There are one load. And there one more load. And one more load. Well, this is a GA, GB, and GC we define, and this terminal is capital A, capital B, and capital C. Then capital A is connect with A in this manner, B is connect B, C is connect this manner. And we define this point as capital N. So we call this system we call this, I think if we draw more clear, okay. Okay, we call this system is so this system is three-phase, three-wire system. Then if in the same configuration, but we adding the wire, one more thing is from small n to large n in this manner. Then we say this system is three-phase, four-wire system. In Korea, this is a 삼선식. This is a 삼성 사선식. And we can define the current here. We can define this current flowing through is I small a large a, and this current is I small b large b, and we define this current is I small c large c. And we have the same current here. This is also I a, I b, I c, but we have one more current, I small. I will give you a written pass like that. So we define the current this manner, I and N this manner. So in the case of a three-phase, four-wire system, the system is very simple. I will give you an example. Actually, there are three sources, but because of this conductor, every load has their own loop like that. So this is one loop, and A phase has this loop, and C phase has their own loop in this manner. So in the case of three-phase, four-wire system, it can be understood that the three single-phase system. So it can be replaced. I mean, it can be decomposed with three circuits, like here, 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 VAS, and AN, GA, VBN, GB, VCN, GC. Small a, capital A, small b, capital B, small c, capital C. The small n, large n, small n, large n, small n, small n, large n. So in this case, IA, I mean the current, this current is IAA, IBB, ICC. And the difference thing is the current of INN. INN is the same, is the sum of IAA plus IBB plus ICC. So we can calculate this very simply. IAA is VAN divided by GA, and IBB is VBN divided by GB. ICC is VCN divided by GC. Therefore, the current INN is the sum of IAA plus IBB plus ICC is a GAVA AN GBVBN GCVCN. So the power, I mean, you need to calculate the power. So total power P is power over PA plus PB plus PC. So if the load GA, GB, GC is the same magnitude of impedance, etc. We call, in this case, in load case, if that, we call this is balanced load. In the case of load, the magnitude should be same and the phasing also same. Then you can say this is a balanced load. If a load balances, in this case, VAN is VP, you define it like that. And the unit is RM is not peak. VBN is then from the here, IAA is VA divided by GA. That will be VP 0 and G theta. So it will be G VP minus theta. IBB is GBVB VP minus 120 G theta will be GVP minus theta minus 120 degree. In the same way, ICC has GCVC AN BN CN. That will be VP 120 G theta minus theta plus 120. Therefore, the current, this magnitude is the same, and phase minus theta minus 120 minus theta plus 120. So it will be also balanced. We call this as a balanced current. Here you know that the source is balanced, voltage is balanced, and load is balanced. Then current also balanced. So from here we can calculate IN. IN here. So IN, we call this as a neutral point current, is IAA plus IBB plus ICC. But this is balanced. Why? GVP minus theta plus minus theta minus 120 plus minus theta plus 120. This is a 0. Therefore, this is a 0. The important thing is, in YY connection configuration, even though it's a 3-phase 4-wire system, balanced voltage and balanced load, then the neutral point current is 0. This is a very important characteristic of the system here. How about the power? We need to calculate the power here. I will give you some space. P is PA plus PB plus PC. PA is V as this and current is this. So because this is RMS, the active power is VP and GVP conjugate, current conjugate. So cosine theta. And PV is VP GVP cosine conjugate theta plus 120. No, this is nothing. I will give you exactly right here. PA is VAN IIA conjugate and VBN IBB conjugate, VCN ICC conjugate. Therefore, it's a VP 0 degree and I is GVP conjugate theta plus VB is VP minus 120 and IVP is GVP conjugate theta plus 120 plus IC is VP 20 GVP theta minus 120. So it'll be eliminate. Therefore, the main thing is 3 GVP square cosine theta. This is a three-phase, the power. So the three-phase power is exactly the 3 times compared to the single phase. This is a single phase power, This is a single phase power. So you multiply by 3. In the case of why use a three-phase system, if we have 3 single phase, meaning we have 1 single phase, 2 single phase, and 3 single phase. We have a load here, we have load here. So power is, we have a VP 0, this is G theta. The power is GVP square cosine theta. Also, this is a GVP square cosine theta, GVP square cosine theta. The sum of them is 3G square cosine theta. And to transfer the power, we have how many wire we need? 1, 2, 3, 4, 5, 6. Through 6 wire, for the 6 wire, we transfer the power this amount. But if we connect this system with 3 phase wire, here, 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 here. If we connect system in 3 phase manner, then we can transfer the same power, 3G VP square cosine theta. But we need only how many? 1, 2, 3. 3 wire. What is more convenient? The 3-phase system is absolutely more convenient compared to the 3 single systems. This is a 3 single phase system. And this is a 3-phase system. 1 3-phase system. We can transfer the same power, but we need only 3 wires compared to the 6 wire. So this is a reason why we use the 3-phase system in the power systems.